All right, well, welcome to Friday. Sign in. All right, how'd PA3 treat you? I looked at a few uploads this morning and they look good, so if that's representative, everyone should be in good shape. So any lingering questions, issues with PA3? Swing buoys, things like that. All right, well, onward to PA4. So PA4 you also have 2 weeks for, and I posted info about the file, about the assignment, but let's just read it from here. Bus showed up.
No, I found it was like $30.
All right, well, since the class just tripled in size, let me ask again. Any questions on PA3 at this point? So my hope is this weekend to get through the midterms and PA3. We'll see if that happens. But I've been slammed since Wednesday, so I did not expect to get to the midterms till tomorrow anyway. But I'm going to do the midterms first, okay, so that those will be graded by Monday, and then I'll do as much of PA3 as I can. So, but PA3, I don't expect there to be any big surprise. I mean, you know what you turned in. If it works, it works. If it doesn't work, it doesn't work, right? It's not like I've got some secret way to break calculator programs or something. So if it looked like it worked to you, you're probably good. All right, so on to PA4. So PA4, you've got 2 weeks to do. You can do this from the command line. You can do it from Eclipse. It's your choice. Actually, I guess I require a zip file, so you got to do it in Eclipse. But you can still develop it on the command line and then just dump it into Eclipse, because you're not required to use Swing or Windows or things like that. Okay. And so if you just write this on the command line, you can just open one file, dump it in there. Should we go over exporting from Eclipse?
Yes.
Okay. Because I had some panicked emails this morning.
Oh yeah. I love it. Last time, and it said
I saw.
your program is going to break for an exception using test.
Yep.
and I panicked and I was like, at 2 minutes before eating, and I was like,
Started testing more. That's awesome. All right, so let's export in the prescribed way. So first thing, make sure you only have one project open. Okay, so is there an easy way to do this? So let's say I want to export this project called voting. So if you have multiple projects open, go to the project that you're interested in exporting, right click, there should be an option for close unrelated projects. That'll guarantee everything else is closed. Okay, if your project's open, you've got this little triangle next to it. If it's closed, you don't. So you probably don't have as many packages as I have in here, as many projects, but make sure this is the only one. Okay, so don't go down into the source, don't go down to the files, don't go into the bin, right? Just on the project itself, right click, and then say export. And then find your general tab, and select archive file. Okay, say next. So this should look like this. You should have the name of your project in the upper left with a check mark next to it, and you should see a .classpath.project file pair with check marks next to them. If you don't, I would say go back and try this process again, because if you do all that, these should end up checked. And if they're not, and you just check them, I can't guarantee that your export's going to be correct. Don't tweak any of the other options, okay? Save and zip, create directory structure, those should be marked by default. So the only thing you want to change here is the path. And I recommend a full path, because otherwise you got to figure out where it created your file. And if you call it, you know, upload.zip, you don't know if you necessarily got the right one. So I'm just going to browse to my desktop, and I'm just going to call it newzip.zip. Alright, and then just say finish. And that should be all you need. So if you go to your desktop, you should have a newzip.zip. If you want to eyeball it, take a peek inside. You should have a folder with your project name, and inside there you should see two files, ClassPath project, a hidden folder, settings, and then source and bin. And if you go down under source, you should see your source code. Alright, so that gets you your export uploaded. If you want to double check whether or not that succeeded, go ahead and I think we can close the project. Right click on the project name and nope, I can't rename here. Okay, so open your project and then right click rename. On some versions of Eclipse you have to right click and say refactor and then say rename. So but on here I can just say rename. I'm just going to call this voting original, and then I'm going to close that. And all of this is just making a copy of this project, because when I import from that file, since my project was called voting, it's going to try to create a new project named voting. And if I already have a project with that name, it will refuse to import it. So I renamed voting to voting original, so now I have no project named voting, and if I try to import that file, it should import. So all my projects closed, okay, and then file import. And this time you want to import existing projects into workspace, not archive file. So existing project into workspace, and then on here select archive file and browse to the file you created. So for me that was newzip. And you should see your project name and it should be checked. That's all you need. Just go ahead and finish. And now I've got my voting project. And I can go into my source and confirm that it's got everything it should have. And then I'm going to get rid of voting original. Does that make sense? Okay. Alright, so on to PA4. PA4, 2-week project done individually. PA5 is going to be a group project. PA4, more individual work. So basically making a version of a 20 questions game, which we started talking about the other day. So 20 questions, the user who's running the program thinks of something, the computer tries to guess what the user's thinking of. Don't program it the opposite way. Okay, that would be interesting. So let me run through this and show you what it looks like. So if I just run this, all right, so think of an object. I'll try to guess what you're thinking of. Can it fly? So what should we think of? A what? A cactus? Cool. Okay, can cacti fly? No. Is cactus, I don't know if it'll do plants. Yeah, we'll try it. I think it's got to be an animal. Could be a kakuna. A what?
Would this be an example of it adding a new node then?
Yeah, I'm not going to let it add though. Maybe I will. A porcupine. Okay, so porcupines don't fly, so we're good. Are porcupines very small? I think they're not very small, so I'm going to say no. Can you ride this animal? Not recommended. Does it have stripes? No. Does it have a curly tail? I've never really looked at a porcupine's tail. Does it like to chew bones? That's probably a dog question. Does it hop? Only if it tries to ride another porcupine. Does it have horns? Does it have wool on its back? No. Long neck. I don't even know if they have necks. Does it live in water? Does it use the sun to keep warm?
Does he?
Yeah. Does it live in a tree? Does it lay eggs? Does it live in a hole in the ground? Does it? Oh, cool.
We should have been animals more about.
It's like after maybe 20 questions, I'm like, are you sure you know this one?
I know. He's Googling.
How well do you know this?
Some species actually live in trees.
Uh-oh.
Oh, man.
This won't be one of those species.
They also live in rock crevices, hollow logs, and small caves.
No.
So I'm going to say not a hole in the ground. Does it like to swing from trees? No. Fur? No. Quills? Yes. Native to the U.S.? Yeah. Native to Arizona? Yeah? Is it yellow? Does it emit a foul odor to defend itself? No.
Wait.
A javelina?
Javelina. Porcupine?
I don't know.
No, it's like a I mean, that's a peccary.
No. They're cute, man.
I mean, they're kind of like porcupines.
Hey, I'll accept it.
Yeah.
Just because
All
it's
right, we're going to say no. What are you thinking of? Possibly misspelled porcupine. Okay, so what's a yes question for porcupine, no for javelina?
Is it a porcupine?
Porcupine.
It's a pro.
Porcupines often live in coniferous forests, so I don't know if that helps.
So it's probably not native to Arizona.
Probably not dead.
Yeah.
All right.
So I've been wearing one.
So it should do better next time.
You better.
Better. Okay, that's interesting. I wonder if porcupine's not in there, actually. All right, so that's what gameplay typically looks like, right? So we're going to talk about the details of this, but as we started saying the other day, it's a decision tree. Okay, so it's a tree. We start with the first root node, and it's a question. We ask that question. We go either left or right, depending on the answer from the user, and we follow this tree until we get to a leaf, and the leaf is our guess. And then if we guessed wrong, we get a new question where yes is the correct answer, no is the thing that we guessed, and we replace the old leaf with this new extra one node deep decision tree. And so when we get to that place where the leaf node was, we'll ask one more question in the future. So you can wire this up to run off of a default database, but it should also accept a command line argument, which is the name of a database that you wanted to work with. So here's my initial database, and I think this is a sample that's actually given in here. So the database format is not something you can easily understand or construct for an arbitrary decision tree. But for a simple decision tree which only has one node and two answers, it's going to be Q colon the root node's question, A colon the yes answer, A colon no answer. But it's really hard to generalize this, okay? So don't try to make a more complex decision tree just by typing in some questions and answers. We'll talk about why this file ends up looking this way. But we can seed the process with a really simple decision tree if we want, just so we're not dealing with a null tree. So here's my sample test file, okay? This is my initial database. So it'll ask one question. Alright, so if I want to run in Eclipse with a command line argument, here's what you do. Click on (20Q), the name of your project, right click, select Properties, and under Properties you'll see something Run Debug Settings. This is where it will say what do you want to run, what class do you want to run main from, and so on. Usually there's only one option here, which is the name of your project. So click on that and say Edit, and there's a tab for Arguments. And so I can list program arguments here. And so I'm going to say /home/nic/test. And then you can apply and OK and apply and apply and close and OK a few times. So now whenever I just hit the run button, it's going to run it, but with that command line argument. If you want to change it, go back through that whole process, change it again. So the way this is implemented, if there's a command line argument, it uses that as the name of the database. Otherwise, it's using a default database, which is this 20-question big database. All right, so I'm going to go ahead and say run. I'm going to say think of an object, and I'll try to guess what you're thinking of. Is it an animal? And I'm going to say yes. And it says, okay, I think I've got it. Is it a pig? And I'm going to say no. What were you thinking of? I was thinking of a dog. So tell a yes, no, for which yes means a dog and no means a pig. So, does it like to fetch? Pigs can play fetch too, that's true. Okay, we'll just go with does it bark. Alright, so now, if I look at my file test, it's grown. And it has answers for dogs, pigs, and rocks. And so, is it an animal? I can say yes. Does it bark? Yes. Is it a dog? Yes. Okay, is it an animal? No. Is it a rock? No. What are you thinking of? A gold-plated laptop. So, question for which yes is a gold-plated laptop and no is a rock.
Is it made of gold?
Yeah. Let's say, can you melt it into earrings? There we go. Alright, so now our database has grown further. Okay, so you got the basic idea. Every time that you stump it, it will ask you for some help, and then it will augment this database, and hopefully the next time you play it will do better. So there's this pre-existing database with 39,786 lines, so about 20,000 questions or answers in it. and it's just tons of stuff. Has it been mistaken for an ugly duckling? A blue-footed booby, another cool bird. Is it a very, 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 very cute, tiny, cute horse? So this has got lots of stuff in it. Squishy sponge. So I've copied this over to Linux under /temp, so 20qbig.txt. And that should be readable by everyone. So you're welcome to take this. Once you feel like your program is working reasonably well, you can start messing around with this. Right? Pull a copy over to your system and play with that and see how it does.
So where we can get this question about that?
Get what?
Question questions.
This? /temp 20qbig.txt. So this file.
So we have to write a lot of questions because we don't know.
You can just copy this file. Just pull it over with SFTP or with WinSCP or whatever you use to go between the server and your own equipment, and just pull that file over. But to begin with, you can just start with you can just begin with 6-line test file. Okay, some more details. When you play the game, first thing it should do is open up the database file, read that to build its tree. Right, so you're starting with a decision tree already in place, which it read from some file, either a file that you specified by default or the file named on the command line argument. So opens up the file, reads it in, builds a decision tree, closes the file, okay, close it as soon as you're done with it, and then play the game. So look at the root, read it as a question to the user, get an answer, follow down to that node, read the next question, follow that down, and so on until you get to an answer node, and then announce that you have the answer, tell the user the answer, find out if that was correct or not. If it's correct, you're good, you're ready to play again. If it's incorrect, ask for the new question that differentiates correct and incorrect answers, build a new node, update the tree, and then write the new tree back into that same file. So every time you play the game, you get to the end. If you were wrong, get new information from the user, rewrite the file at that point. So now you can go back and you can play again and use the new tree, or you could exit at that point, come back in, and you'd still have the augmented tree. So your overall flow is open database, build the tree, play the game, if the final guess was correct, then you can just go back and play the game again. If it was not, get a new question and answer, update the tree, and write the database, and then go back and play the game again. And you can go right back and play, or you can ask the user, do you want to play again, or whatever you choose. Like with PA3, the style of the program is your choosing. Okay, you can do it all on the command line, you can do it all through a GUI, you can have a mix, You can, have different options. You can show a history of questions and answers on the side. It's totally up to you. But I do want you to update the database on the drive at the end of each time that you go through. If you got the wrong answer, update the tree, write it out to the file. And your code should be well commented, etc., all of that stuff. All right, so let's talk about this file. So what's our tree look like right now? So this is a tree that we just built up, right? Dogs, pigs, gold-plated laptops, and rocks. And this is the file that got written corresponding to that. So, is it an animal? Does it bark? Dog, pig. Can you melt it? Laptop, rock. This is all going to be recursive. So here's what the file had. Is it an animal? That's the root node of the tree. Does it bark? That's the root node of the left subtree. Dog, that's the root node of that left subtree, right, which is an empty tree. And then pig, which is the root node of the right subtree of bark. And then can you melt it, which is the root of the right subtree of the root. And then laptop on the left and rock on the right. So best guess, what's the traversal order for the tree going into this file? What?
Node left, right?
Node left, right. So writing the file, very, very simple. Traverse your tree in node left, right order and write everything out into the file. And there's one detail on the formatting. Each line of the file begins with either a Q colon or an A colon, right? And the next line is either the question or the answer. So each node in your tree basically occupies 2 lines of the file. So Q colon is an animal, Q colon does it bark, A colon an answer, and so on. So in your tree itself, it may be useful to have a flag which says, is this a question or is this an answer, right? Something that lets you know whether this is a leaf node, basically. So let me just write down next to each of these, this is a question, this is a question, this is a question, and these are answers. And so when you traverse your tree, take your first node, see whether it's a question or an answer, write out Q colon or A colon accordingly. New line, write out the data, new line. And then call your output function on the left subtree if it's not null. And then call your output function on the right subtree if it's not null. So totally recursive. Standard node left, right. Okay, on writing the file. node left right traversal. Reading the file is a little more bizarre, because we're trying to do a node left right kind of in reverse. So here's my suggestion for reading. So we have this file. Open this thing up with a scanner. Okay. Don't pass anything to your read method. Your read is going to recursively ingest this file, and it's just going to pick up wherever we left off. Right? So if we read down to where it says answer pig, the next time that we call read, it's going to start with the Q colon, can you melt it into earrings? Okay, so you can pass the scanner object if you want, but don't keep closing and reopening the file inside this ingest process. Okay, open it once outside of the whole read method, and then call your recursive read method. And this should return a tree, or maybe a tree node. Let's say it returns a tree node. All right, so what does this do? So read the next line of the file. And if what it reads is A colon, then there's an answer. So so read the next line after that. Save that as a new tree node. Set the left and right children of that tree node to null. And then return that node. So when you call read, if the current point in the file is A colon, you're just going to read that. You're going to read the next line, which is the actual answer, make a single node containing that answer, return that node. Okay, otherwise you read that line, and presumably it's a Q. If it's not a Q or it's not an A, your file is corrupt. So if it reads that and it's a Q, then read the next line. Save that as a new tree node. So set the data portion equal to the question you just read. Here's the fun part. Set left equal to the return value from calling read again, and then set right equal to the return value from calling read again. So this is where it recurses. So one way to think of the read method is it starts at whatever place you are in the file, and it reads a decision tree from the file starting at that point. Doesn't necessarily read the entire file. It simply starts wherever it is in the file and reads as much as it needs to build a complete decision tree from that point down. Bless you. So let's look at our test file. So our test file says, is it an animal? Does it bark? Dog, pig? Can you melt it into earrings? Laptop, rock. So what does our read process do? It says read the first line, okay, and it's a question. So it's going to make a node, and the data there is going to be, is it an animal? Okay, and we've read this, so now we're sitting at this point in our file. And now we're going to call read, and whatever read returns, that's going to be the left child of this node. Okay, so we're going to call read, and it's going to create a node that contains bark. So we read this, it's a question, so we create a new node. We set that equal to bark. And now we're sitting at this point in the file. We're going to call read, and whatever read returns, that's going to be the left child of bark. Alright, I'm changing colors, but it doesn't show up there. So we call read again, and it reads the next line from the file, which is this entry, and that's an answer. So since it's an answer, it's going to create a node. The value is going to be equal to the answer. Left and right are going to be null, and then it's going to return this node. So we come back from this latest call to read, which was saying call read and set the left child equal to that node. So the left child of bark is equal to dog. And then the other part of dealing with a question is call read again and set the right child equal to what that returns. Well, we call read again, it's sitting at this point in the file. That's an answer, so it creates a node, which is pig, sets the left and right children to null, returns that node, and so our call to bark says set the right child equal to pig. Now we return from our first recursive call to read up here, which said call read and set the left child equal to the result. Well, that first recursive call is going to return this node that it created, and so this is going to set the left child equal to that. And then there's a second step when we find a question, which is call read again and set the right child equal to that. And the process repeats. So we read this, that's a question, so we're going to create a node, melt. We're going to call read and set the left child equal to it. So we'll call read, we'll see an answer, which will be laptop. It'll return that as a node value. We come back to this read, it read and assigned the left equal to that. Now it's going to call read again and assign the right equal to that. So we did laptop, so it'll read rock, create a node with that value, return it. Now that's the right value of melt.
So it automatically continues off of the previous 9. There's a lot of people need to do.
Yeah, as long as you don't close the scanner or do any extra reads, it should just continue where it left off. So now our one recursive call to our first recursive call in the beginning of read ingested and assigned the left. We just did a second recursive call which created all of this and returned that, and we assigned the right equal to that. And now we just return the root of this. And we're done. Our call to read from our main method has returned the root of this decision tree, and miraculously we've ingested exactly every single line that's in the file. If we were to do one more read, we would find that it has no next line. So this will work, but it's feels weird or feels really good depending on how you like recursion, I guess. So the read method, read the next line. If it's an answer, read one more line, save it as a node of a new tree node, set its children to null, return that new node. If you read a line and it was a question, then read one more line, save that as a new tree node. But before you return it, call read 2 more times. Call it once, set the return value to be left's value. Call it again, set right equal to that return value. And as I've said, if you just go in here and you try to sort of figure out, you know, shouldn't that question come after that and so on, you can do it, but you've basically got to do all of this, right? And for us, it's usually pretty confusing. Going from a decision tree to a file, we can sort of do in our heads or on paper, but going from this to a decision tree, not always clear, especially when you have a really big file. So you may see 15 questions in a row, right, followed by 2 answers, followed by a bunch more questions, followed by, you know, 35 answers. And that may be perfectly fine. It just depends what your decision tree looks like. But a way to check it if you want to play with the process is to take this and try to do some ingesting. And I don't feel like we have time today, but Monday we'll spend some time on the board playing 20 questions, but mainly updating these decision files to make sure that part is working. And then we'll probably spend some time doing some ingest on some smaller files. So let's run this once more. Is it an animal? Yes. Is it a pig? No. What were you thinking of? A dog? Does it bark? Alright, think of an animal. Is it an animal? Yes. Does it bark? Yes. Is it a dog? No. What were you thinking of? A seal? Does it live in water? So here we got 3 questions in a row, and then we got 4 answers. And so if I was reading this with the recursive read function, right, first I would see, is it an animal? And then I would say call the read method and take the tree that it returns and set that equal to the left child. And that recursive read method is going to ingest all of this. Okay, these 2 questions, these 3 answers. That's all going to get tacked on to the left. And then I'm going to call recursive read method once more and say set my right child equal to that, and that's going to eat up these 2 lines, which is answer rock. But if you believe this works, you don't actually have to understand why it works, but you'll want to know that at some point in the next 2 weeks, I'm pretty sure anyway. And convincing yourself to some degree that this works just kind of helps more with recursion and kind of being at peace with the universe. All right, does that make sense? Enough sense to get going? All right, you're allowed to start with an initial decision tree. When I test your code, I will start with a 6-line database file. Okay, I won't start with an empty file because that's just kind of an edge case. So I'll always start with this, and then I'll play the game, expect it to play, and expect it to grow. I'll also test it with the full database just for kicks. Make sure your yeses go on the left and your no's go on the right. Okay, otherwise it's not going to work with other databases. And then, yeah?
Do you want us to restrict the depth of our tree to 20 questions?
No, so you don't have to limit to 20 questions. But you're welcome to keep track of how many questions it takes and gloat about that appropriately. So pieces you can use to develop this sort of systematically. Obviously, you're going to need to implement a binary tree. Okay, so that's not a bad thing to start with, but it's not terribly exciting to just have a tree class without something to do with it. So, binary tree class, you can hardwire some nodes if you want. You can make a hardwired tree. You know, make a node that's equal to animal, make the left child a node that's equal to dog, make the right child a node that's equal to a rock. And that should be enough to play, you know, a one-question game. And so if you want to start working on the interaction with the user, where you read a question, get an answer, follow the tree, and so on, right, you can do that without worrying at all about the database process. You can just write some statements to cobble together a tree, like we did in some of the ODPs for 222, and then just use that to play your game. So there's playing the game, there's updating the tree at the end of the game, and then there's reading and writing the tree to the hard drive. And those are sort of the three main components to this, plus all the bells and whistles and polish. Playing the game is probably a good first thing to go with. Updating the tree is simple to do on paper, but takes a little bit of work. So let's say this is your tree. So is it an animal? Yes. Does it bark? Yes. It's a dog. No, it's a cat. If it's not an animal, it's a rock. So you come down here and you get to cat, and the person says, no, it's not a cat. Okay, so you ask what they were thinking of, and they say they were thinking of an elephant. Okay, so you need to make a new single root, two children tree. And you're going to ask for a question. Yes is an elephant, no is a cat. So, is it large? Larger than a cat. So you build this tree, make a new node, set the data equal to their question, mark it as a question with your flag, set the left child to a node containing the correct answer, right child is the incorrect answer. And then you need to replace this node with this node. So you have to know what the parent of this node is, because we can't just take this node, which we call temp, and say temp equals this new node, because that doesn't change the right child of bark. This is what we really want to change, is the right child of this node. So you got two options at least. One, as you're traveling through this tree, you can remember each node before you move down to the left or the right. Remember where you came from. And then when you get to the point where you've got to replace a node, you can say, where did I come from, and set the left or right child equal to this. So you also need to know which way you went the last time that you moved down from where you came from. Did you go left or right? The other option is just make a tree with back pointers. And since we're not doing any deletions, that's not a bad thing to do. And then when you get down here and you say I want to delete, well, you can just follow the back pointer up and go from there. So that's got some data structure details to work out. All right, good for the weekend? All right, have fun with this. It's fun when you get it working, even when you get it nominally working, because you can play 20 questions with it and you can impress people. All right, have a good weekend. I will see you Monday.